Hello, everyone.
Hi.
Massimo, are you there?
Yes.
Thank you. Yeah, so I think we are just exactly on time for the afternoon session. So, if you want to start to share your slides.
Okay.
Okay, so the first speaker of the afternoon session is Massimo Meneghetti from INAF, Osservatorio Astrofisica Scienza dello Spazio di Bologna. He will talk about strong lensing constraint on the small scale structure of galaxy clusters. Go ahead, please.
Yeah, thank you very much. First of all, for the possibility to attend, even if only virtually, this event, and to speak about the work that I and my collaborators that have been, the collaboration has been already introduced this morning by Piero are doing. So here I want just to show this slide that allows you to attach some faces to the names that you have already read this morning in Piero's presentation. Yeah, so in my talk I will cover a few topics that basically well described in a series of papers that our collaboration have produced in the last years. This is a kind of a summary of where you can read about our work. Actually, Piero already discussed a lot of this morning. So basically, these two first topics that regard the usage of the data and the techniques that we use to model galaxy cluster using strong lensing and also combining strong lensing with the galaxy kinematics data have been already extensively described by Piero. So I will go through this stuff very, very briefly. And I will focus instead of the last topic in this list, which has been already anticipated also by Piero, which is some recent work on the small scale structure of galaxy clusters and what we could learn about the small scale structure of galaxy clusters. In particular, I will talk about an excess of small scale gravitational lenses that we have observed in the cluster that we have reconstructed compared to what is expected from theoretical expectations in the framework of the cold dark matter paradigm. All right, so this is basically the focus of the talk. So small scale structure as traced by particular kind of strong lensing features that we can observe in galaxy clusters that are what we call the galaxy strong lensing events in galaxy clusters. So we're not talking about this tangential arc or radial arcs, these big, very, very big features that you usually think about when you talk about strong lensing by galaxy cluster. Neither about the sets of multiple images that Piero mentioned today, and that we found in the systems that usually are multiple images of galaxies in the background of the cluster produced by the overall mass distribution of the cluster itself. We're talking about other kind of events like those that you see in these three zoom-ins in this image of the galaxy cluster Max J1206. So events produced by cluster galaxies that are lensing some background source. Okay, so not the overall mass distribution of the cluster, but the mass which is concentrated in galaxies that belong to the cluster. And these are three examples, as I was saying. So, for example, if you look at this image here, you see a cluster galaxy that is lensing a background blue galaxy, forming this kind of Einstein ring. The source here is a redshift 1.4, while the cluster is a much smaller redshift. Here you see another galaxy forming three different images of another source at redshift 3.7. And here you see another galaxy forming 4 images of a Lyman alpha emitter at redshift 5. Okay. This is not even detectable in the HST data. This is detectable in the news data cube that we used in combination to the HST imaging to study this system. And you see these strong lensing features here, they form around some lines that are here shown in white that are called the critical lines. You see that the cluster itself has a large critical line, but then several of the galaxies that you see here have their own critical lines, those that we call secondary critical lines, because they are attached to secondary lenses in this system. And these strong lensing features, they form around them. The size, the typical sizes of these systems that we discovered in this cluster, for example, is of the order of a few arcseconds. Okay, the large-scale features that you see here, for example, the form of these arcs here, they measure tens of arcseconds, so much smaller than what you typically think about when you talk about strong lensing by galaxy clusters. And the masses of these lenses here is of the order of 10 to the 11 solar masses. Okay, so the fact that you have many of these galaxies here that have their own critical lines means basically that this is a prediction of our strong lensing model. It means basically that potentially all of these galaxies here could produce strong lensing effects like those that you see in these three examples. Okay, and studying this kind of effects is very important because the ability of clusters to produce events like this can be used as a metric of how the dark matter is distributed in the substructures that are hosting the cluster galaxies. Okay, this is the main topic of this talk. And essentially, by comparing mass distributions recovered from observations like this one to what is instead produced from numerical simulations, that now have reached quite a high level of complexity to account for all the physics that is relevant to describe how galaxy clusters form and evolve. One can, for example, check if the properties of clusters, like the small-scale structure of cluster, is or not consistent with the properties of the substructures of the subhalos, the dark matter subhalos that we can measure from these mass distributions of simulated objects in the framework of a particular dark matter model, for example, in the framework of a cold dark matter. And there are several features that we can compare, like, for example, the mass function of the subhalos, the radial distribution function of the subhalos, their mass profiles. What we want to do here is to basically summarize all these properties that affect the strong lensing ability, the ability of the subhalos to produce strong lensing features into one particular metric that we will use essentially to characterize the small-scale structure of galaxy cluster, which is their ability to produce galaxy-galaxy strong lensing events. Okay, so in this work, basically, we are going to use a set of observed clusters that were already, as I said, introduced by Piero in his talk today, that have been investigated in depth, combining HST imaging data, mainly coming from some large HST programs like the so-called frontier fields and the CLASH programs that have been producing very in-depth observations of galaxy clusters, of strong lensing galaxy clusters in the course of the last decade. In combination with spectroscopy data from several VLT instruments like VMOS and MUSE to produce very precise and accurate models of cluster mass distributions down to the scale of galaxy scale subhalos. This is particularly true for a subset of these clusters, for which we could use, as Piero explained this morning, the galaxy kinematic measurements to constrain better the mass distribution in the cluster galaxies. So these are 4 mass models of clusters that we have reconstructed using this particular technique, combining strong lensing and kinematic constraints. Okay, so this will be our reference observational data set to compare to numerical simulations. And for what regards the numerical simulations, what we have been using so far is a set of simulations produced by our colleagues in Trieste, which is called the Dianoga simulation suite, which is an ensemble of 25 massive galaxy clusters simulated in the context of a lambda CDM cosmological model that basically have the characteristic to match very well the many properties of the clusters that are in our observational data set. So, for example, their mass, their concentration, their central surface density, their ellipticity are very similar to those of our observed clusters. And we use these 25 galaxy clusters observed at redshift similar to what of the redshift, of the cluster that we have observed, to produce a large set of mass distributions, hundreds of projected mass distributions that we basically can compare to the observations. So some of the most important properties of the simulations for this work is that the simulation, they have mass resolution of the order 10 to the 8 solar masses, and the force resolution is of the order of a few kiloparsecs. So they are suited to resolve the masses of these systems that I showed you in the beginning, in the first slides, the galaxy scale systems that we have seen to produce strong lensing events in our observed clusters. And another important aspect of the simulations is that they are hydrodynamical simulations in which it is implemented a galaxy formation model that includes a lot of the physics which is relevant for describing the processes that lead to formation of stars, to the release of energy in the intergalactic medium via, for example, supernova explosions, AGN feedback, and all of these effects have a strong impact on also on the underlying dark matter that we see in these objects. And it is important that the baryonic physics is well reproducing some observable properties of galaxies in clusters. So our simulations have been tuned, in particular, the galaxy formation model, which is implemented in this simulation, has been tuned to reproduce some observable properties of galaxies in clusters, like, for example, the high mass end of the stellar mass function of the galaxies in clusters, okay, or the Magorian relation, so the relation between the black hole mass and the stellar mass of the host galaxies. And not all the simulations have these characteristics. So there are simulations in the literature that are known to fail in reproducing some of the properties of these galaxies. Like there are simulations, and we'll come back on this issue later, that tend to produce, for example, very massive galaxies that we don't want in our analysis, because basically this is what the scale that we want to probe, right? So we want this galaxy to be as realistic as we can. Okay, so in these two diagrams here, you see, for example, these empty diamonds that show some bright galaxies forming in simulations of galaxy clusters and groups that are too big compared to observations that are shown here by the black stars. Okay, we don't want this. Our simulations indeed corresponds to these blue points, blue circles that you see in these two diagrams. All right, so I told you that we want to use a galaxy strong lensing as a metric to quantify the distribution of dark matter on the scales of cluster galaxies. So to define this metric, I need to introduce you a couple of lensing quantities that are what we call the caustics and the critical lines of the lens. Okay. So what you see in this image here is the mass model of MAXA 1206. You see here in blue is the footprint of the HST observations that we used to build this model. And now we do this exercise. So we use this mass distribution here, and we use it as a lens to study how we can propagate towards distant sources some light rays that we shoot starting from our position, which is here, through this lens plane. Okay, these here shown from the side. So we have these light rays that propagate through the lens plane. They get bent, and then they convert to some positions on the source plane. And here you see what happens to this field of view when you do this kind of exercise. And you can see that when we move from the lens plane towards sources at larger and larger redshift, this lens plane basically shrinks. No, so we basically focus the light rays into a region which is much smaller than the one from which we started. And in particular, we have regions where a lot of light rays tend to converge, forming this kind of structures here that they are called the caustics of the lens. Okay, and these caustics basically are the equivalent of what you see on the seafloor when you observe the light of the sun crossing the water in the sea. Okay, from these regions of a very high light concentration that are the equivalent of these caustics here. And these are the envelope of these caustics here are basically defining regions where we have multiple light rays that propagate hitting the same position. Okay, so for example, these two solid light rays here, they propagate through the lens plane, passing on opposite sides of the lens, and they get deflected to arrive to the same source position here. So in this case, we would observe from our position two different images of this source appearing here and here with opposite parity. So one is the reversed version of the other. Okay, and indeed this is explaining how we form multiple images in a strong lensing event. So if we place, for example, a source, this red source here, inside this caustic of the cluster, and then we do the reverse operation. So we move our light rays back to the observer. What happens is that when we basically unfold the sky, we form large arcs like this one. Okay, so this explains the mechanism to form these strong lensing features here. Okay, but you see, these are strong lensing features forming around this very large critical line, okay, which is the corresponding of the caustic on the lens plane. And this is the corresponding critical line to the large caustic where we placed the source in before. This is the main critical line of the cluster. But there are a lot of other critical lines here that are those critical lines that I was mentioning before, where we can observe, around which we can observe strong lensing events on galaxy scales. So if we go back on the source plane, you see that these critical lines, they correspond to secondary caustics that are basically locations where if we put a source, we would produce this kind of strong lensing features. So if you want to quantify essentially what is the ability of this cluster to produce these strong lensing features, we would need to measure the sizes of all these caustics here, and summing all these areas that are contained into these caustics, we would define the so-called cross-section for these galaxy strong lensing events. So this is basically what we do to quantify how the matter is distributed in these subhalos that host these cluster galaxies in our analysis. So this slide here shows you a summary of our procedure. So what we do is start from the mass distribution of the lens, either the observed one or the simulated one. And we identify all these critical lines, the secondary critical lines. We map them on the caustics, and we measure the sizes of the caustics, the secondary caustics. And then if we basically measure this total cross-section in this way, and if we divide this cross-section by the total area, which is sampled by our observations, then we determine what is the probability for galaxy-galaxy strong lensing. And this is the metric I was talking about. This is the metric that we want to use to quantify essentially how the dark matter is distributed on these scales. So we did this kind of measurement of this galaxy-galaxy strong lensing probability for both the recovered mass distributions from the observations and from the simulations. And when we compare them, we found this quite interesting result, which is shown in this diagram here. Here you see the galaxy-galaxy strong lensing probability as a function of the redshift of the sources. And what you see here, for example, in dark blue, is the galaxy strong lensing probability, the galaxy-galaxy strong lensing probability that we measure in our observed sample, in our reference sample. And the other violet and blue curves, they show some other measurement done on other samples of cluster for which we don't have, employed our technique to combine the galaxy kinematics measurement and the strong lensing constraints to build a mass model, so they're less reliable. But nevertheless, these lines here, they are basically much higher than this other line, this dashed line here, that shows basically the same quantity, the same metric for the simulated clusters. So there is a difference of about a factor of 10 between the observations and the simulations, telling us that in observed cluster, we have a probability of observing galaxy-galaxy strong lensing events that is higher by a factor of 10 compared to what we expect in this framework of the cold dark matter scenario. Okay. So how do we interpret these results? Basically, these results tell us that the internal structure of the subhalos in observed clusters is very different from the internal structure of similar subhalos in the simulations. You can see that also by high, that essentially these subhalos in the mass reconstructions that we obtain from strong lensing and galaxy kinematics are more compact than what you typically see in similar simulated clusters. Okay, and we can quantify this difference also in terms of a proxy of the compactness, which is the maximum circular velocity of the, for example, of the stars of the matter particle in these subhalos. And you see, observationally, we find this black line showing you the relation between the maximum circular velocity and the mass of the subhalos, while all these colored points here, they show measurement of this maximum circular velocity and mass of the subhalo for subhalos in the simulations. Okay, so they are systematically, all these measurements are systematically laying below this observed relation. As I said, this maximum circular velocity is a proxy of the compactness of the subhalos, and this is showing us that also not visually, but also quantifying it, that simulated subhalos are less compact than their observed counterparts. Okay, and because they are more compact, they can also resist more effectively to, for example, tidal stripping, many dynamical processes that affect their existence within the gravitational potential of the cluster. And in particular, we find that they can survive also in very dense regions of the cluster, like the cluster center. So if we compare the radial distribution of these subhalos in the simulations and in the observed cluster, we find that subhalos in the observed clusters are generally more abundant near the center of the cluster, where they can produce the strongest strong densing effects because the background density there is also higher. Okay. So this was a quite interesting result, I think. We would like to give an explanation of this, so understand what is the main difference between the observations and the simulations that is causing this kind of discrepancy that we are highlighting with this new metric. So when we found these results, we made two basically assumptions. One is that maybe we are missing something about the nature of dark matter. We are treating the dark matter as cold dark matter. Maybe it's not cold dark matter. We need some other kind of particle candidate or some other sort of dark matter to explain this discrepancy. And the other option that the other hypothesis that we formulated is that maybe there are some limits in our simulations that we haven't realized yet. There were a few papers that came up after our first paper in 2020 that questioned the resolution of our simulation and some properties of the galaxy formation model that is implemented in our simulation. So we did recently a lot of work to study in depth these two issues, and this is what I will talk in the rest of my talk. I want to show you first of all this slide that describes how the resolution of our simulation is okay and cannot be the reason for the discrepancy that we are finding. So what we have done in the past few months is to create a sort of grid of simulations of starting from the simulation that we used in our original paper, and studying the same objects simulated with different resolutions and different galaxy formation models. So this slide here shows you what happens to a particular cluster when we simulate it with a resolution, with a mass resolution, which is a factor of 10 and a factor of 25 higher than our original resolution, on which the results that I've shown you before are based. Okay, so here what you see is the mass distribution of the cluster with overlaid the critical lines along which the strong density feature should form. And if you compare, for example, the number of these critical lines and their sizes, you immediately can notice that there is not big difference between one realization and the other realization at higher resolution of the same object. And indeed, if we measure the variation of the galaxy strong density probability as a function of the resolution, we basically find no difference. Okay, so increasing the resolution doesn't increase the galaxy strong density probability that we can measure in the simulations, and doesn't allow us to match what we measure in the observations in particular. Okay, so resolution cannot be the issue here. The other aspect I want to talk about, the other aspect of the simulation that we have investigated that I want to talk about is the particular ingredient of the galaxy formation model, which is the scheme which is used to describe the phenomenon of AGN energy feedback. Okay, so when you have a supermassive black hole at the center, for example, of a galaxy, it accretes mass and it releases energy in the intergalactic medium. And this energy, which is released, has a quite strong impact on how the simulation and the galaxy will form stars, right? Because the more energy you release, the more you suppress the gas cooling, and the lower will be the star formation efficiency. Okay, so if you instead reduce the AGN feedback efficiency, then you will, of course, form more stars. So if you form more stars, you will have a larger concentration of mass at the center of the galaxies forming in the simulations. And because of adiabatic contraction, you will also drag more dark matter in the center of these subhalos. So you will make dark matter subhalos more compact and more efficient than to produce strong lensing effects. And indeed, in this exercise, where we compare 3 different schemes for implementing the AGN feedback, we notice exactly this kind of effect. So you see, there are 3 realization of the same cluster in these 3 images, obtained by adopting 3 different schemes for AGN feedback that are very different implementations. I will not go into the details of this implementation, but the most important difference between these 3 models is that these 2 models, and this one is the one that we used in our original simulations, have more or less the same effective efficiency at suppressing star formation in the simulations. Okay, while this other simulation here is based on another scheme, which is taken from this paper, Massimo et al. 2020, that is much less efficient at suppressing star formation. Okay, and for what I just said before, in this particular situation, we tend to form halos that are more compact, and indeed, when we measure the galaxy-galaxy strong lensing probability, you see that we gain a factor of 4 on average with respect to these other simulations here that are pretty similar. Okay, so different implementations of the feedback effect produce the same result, provided that the overall efficiency for suppressing star formation is the same. If we reduce the star formation if we reduce the efficiency to suppress star formation, then you form more, more compact subhalos that have a larger probability to produce galaxy-galaxy strong lensing events. So one could think that then if we reduce the feedback in the simulation, then we solve completely the problem. This is not true. So already in our paper in 2020, we had considered this possibility of switching off the AGN feedback in the simulation to see what happens. And essentially what we noticed was actually an increment of a factor of 10 in the galaxy-galaxy strong lensing probability. But, doing this kind of operation has a lot of drawbacks because essentially what happens in this simulation is that we tend to produce galaxies, as I pointed out at the beginning of my talk, that are completely unrealistic. In particular, if we look, for example, at the stellar mass function and the masses of the brightest galaxies in these simulations, they tend to be too large compared to what is observed. Okay, and the fact that we produce a very, very big, very massive galaxies in these simulations, of course, has an impact on the strong lensing, on the probability for galaxy-galaxy strong lensing effects, because we tend to produce in this simulation some super lenses, like, for example, this galaxy here or this other galaxy here, that have extremely large critical lines that are not present in the observational data set. As you can see, the sizes of the critical lines that we observe in real clusters has this very sharp cutoff at about 3 arcseconds in size, while this simulation that produce these big galaxies, they tend to produce also critical lines that are much bigger, up to 10 arcseconds, let's say. And these objects here, these few objects here, they tend to dominate the budget for the galaxy strong lensing cross section. Okay, so the factor of 4 that
5 minutes, Massimo.
yes, sure. The factor of 4 that I mentioned before is only an apparent gain, because most of it is due to these large objects. Instead, if we look at the scales that are relevant for galaxy strong lensing, so the masses of the subhalos around which we observe strong lensing features, here we don't see very big differences in terms of, for example, of maximum circular velocities. Only at the very large masses we observe this kind of strong effect of reduced feedback from AGNs. Okay, and therefore also this kind of modification of the galaxy formation model cannot be the solution to the problem that I showed you before. Essentially, because at the scales that are relevant for galaxy strong lensing, from the observational point of view, the subhalos in the simulations continue to be less compact than their observed counterparts. So the simulations that have a reduced feedback will basically produce a compact subhalos, but only at very large scales, where we don't basically have any observed galaxy, or very few observed galaxies. Okay, so this was essentially my last slide, and these are my this is my summary and my conclusions. I think I showed that strong lensing is a powerful tool to unveil the inner mass distribution of galaxy clusters, and in particular to study the distribution of matter and dark matter also on the scales of galaxies and galaxy clusters. I showed that a comparison between observations and simulations in the context of the lambda CDM has evidenced the presence of an excess of galaxy strong lensing events in observations compared to simulations. And the origin of this excess is still unclear. It may be caused by other unknown systematic issues with the simulations that we haven't understood yet, or, and this is more important and more interesting, of course, could be some incorrect assumption on the properties of that matter. So solution can be found in the dark sector on this aspect. Okay, so I think I will stop here. Yeah, thank you very much for your attention.
Okay, thank you, Massimo, for these very interesting results. And let's see, we have some question from the audience. Yes, we have a question. Jorge, please go ahead.
Thank you, Carlos, and thank you, Massimo. I just more a comment than a question. I think that these results make a lot of sense for us, as you know, Carlos, because when we introduce the cutoff in the phase space or in the phase space distribution of fermions, for example, in the case of our model that can parameter of mass particle evaporation, let's say, that could simulate this kind of effect of interaction that can occur in the clusters. The phase space distribution functions change in such a way that the configurations becomes more compact, not only more compact, but also more dense toward the center of the distribution. So for us, at least in our model, this makes a lot of sense. So just to comment this. Thank you, Massimo.
Yeah, thank you, Jorge. Maybe I can comment on top of this. Indeed, I have a question, and maybe I will relate link my question to the Jorge's comment, because one thing I also wanted to ask to Piero was about I know this is very recent result. This is a comparison with lambda CPM showing this tension, but I would like also to know if there are attempts or have been attempts to tackle this problem from more generic cosmological simulations. For example, one of this cosmological suite simulation of ITOS program, which accounts for for interactions with the dark sector in such a way that have some similitudes with the warm dark matter, considering this cutoff. But I think that from what I understand on these more general simulations, either more warm-like dark matter or self-interaction, still, as far as I understand, the tension will remain because this is showing an even more concentration of substructure differently with this interaction model, which tends to put, let's say, put a cutoff in the power spectrum. Could you comment on this, please?
Yes, indeed. Essentially, the models that you mentioned before, they were developed in particular to try to solve other, let's call them dark matter crises related, for example, to the abundance of SUBHALOs or satellites in the neighborhood of our galaxy, or that were not reproduced by simulations, or the problem of the flatness of the density profile of some observed galaxies. But these are basically problems that somehow go in the opposite direction to what we're going.
Yeah, exactly.
So these models would even make probably worse the comparison to observations on the scales. Although there are some issues that, for example, in simulations employing some dark matter models that are alternative to CEM have not been considered properly, maybe in the past. For example, making the example of self-interacting dark matter models. In this, most of the simulations that were developed in the past were not including also hydrodynamics. And more recent simulations on much smaller scales actually are showing that self-interacting dark matter in presence of baryons that condensate, that cool and condensate forming stars could produce some kind of compact cores due to gravothermal collapse that could go in the direction of that we want.
So
okay.
I see. So you are talking about the analogous effect evidenced in some globular clusters, but at a very different scale, which is a cluster of galaxies. You mean this fact of the dark matter can undergo kind of in the direction of gravothermal catastrophe, of course, then being stopped by other processes. There are some speculation that may be taking place here, you mean?
Exactly. So I think, I mean, we didn't make any, well, actually, we started to produce some simulations of galaxy clusters in alternative models, like self-interacting dark matter model, trying to see if, for example, adopting a cross-section for self-interactions between dark matter particles that has some dependency on velocity and the velocity of the particles in the SUBHALOs. We can produce this kind of gravothermal collapse on the scales that are relevant here. At the moment, we haven't succeeded in doing this. So I think we will need to explore many other alternatives.
I see. Yes, then I also coming back to the Jorge's question and your answer, I think it's just an opinion, a comment that it may be also linked with the sometimes called diversity problem of profiles, and maybe some underlying physics that we still don't understand that are causing not a universal profile at all galaxy scale, but some diversity. For example, the model we are working on, which is based more on a maximization of a coarse-grained entropy, which, by the way, this is a subtle problem in n-body simulations, because due to the effective particle masses that are used in the simulations, imply some softening length and some conversion radius, which are not yet, which are effective sometimes parameters put in this n-body simulation, which, considering that they want the simulation to be in terms of collisionless dark matter, they don't allow to the conversion radius to be too much inside. Otherwise, you may start to see some chord profiles. But just to say that that still are open issues about the relaxation of halos in n-body simulation. But when you go in that direction, for example, the work we are doing for fermions, you see this diversity of halo tails. This is interesting, what Jorge was saying, because as you probably remember, we have shown that there are a family of possible solutions from polytropic light, which are the most compact. These are clearly more compact. As you know, polytropes are more compact because are steeper than power law. For example, R2-3, which is typical of NFW. So this will automatically cause more compact halos in substructure, for example, in galaxies of 10 to 10, 10 to 11 solar masses. And yeah, I think just to say that I think it will be very interesting to test these observations with this more compact halo arising from this maximum entropy production.
Yeah, definitely. I mean, it should be very, very interesting to try these other models. So yes, we should find out a way to produce some mocks implementing this diversity of profiles and see what we can obtain.
Yes, I think hope we can continue this discussion in the future, and why not to try some collaborations that we have chat on some point that it will be interesting if we can continue in the short future. So yeah. Thanks a lot, Massimo, and I don't know if there are any other question in the audience. Otherwise, we are just on time to. Okay, we thanks Massimo then, and we should go to the next slides, to the next speaker, Valentina CRESPI. Are you there?
Yes, I'm here. Hello.
Good. Yes, perfect. So if you can start to share your slides.
Yes. Do you see them okay?
Yes, yes, perfect. Okay, so now we have Valentina CRESPI from La Plata National University, Argentina, and the Instituto Astrofísico of La Plata. And she will talk about S2 star dynamics in high dark matter density around Sagittarius A star. You can start.
Yes, thank you. I'm going to talk about, in particular, this star of the S cluster, the S2 star, and present you the results on our last work in Argüelles and Collaborators 2022, where the collaborators are listed here. And these results are on the precession of the S2 star in a particular dark matter model, which you've been hearing about this morning, the Ruffini, Argüelles, and Rueda model. So first, let me begin presenting this model briefly. So these dark matter halos, composed of uncharged fermions, form from a maximization of the entropy principle, in which one can find a distribution function, as Carlos talked about earlier. So in this model, we have 4 free parameters, which are the mass of the fermions, and 3 dimensionless parameters. First, we have the temperature parameter. Theta is the degeneracy parameter, where here mu is the chemical potential, and a cutoff parameter, where epsilon here is the kinetic energy of cutoff. So this this RAR model, extended RAR model, extends the original one by allowing these halos to be more realistic because they are bounded in sizes and masses. So sufficiently energetic particles, which energies above the cutoff energy, can escape this configuration. So for these fermions, we have a distribution function, which is the one of Fermi-Dirac, with a cutoff in the energy momentum. So we also model these fermions of a perfect, which are in a perfect fluid, as a perfect fluid in hydrostatic equilibrium. So for them, we have the energy momentum tensor of the perfect fluid, where the density and pressure are given by these expressions, and they are obtained integrating over the momentum space the distribution function until the cutoff momentum. So with this in mind, in order to find the equations of this model, one has to solve the Einstein equations, where here the energy momentum tensor is that of the perfect fluid, and we have for this geometry spherical symmetry and also static. This is a static spacetime. So with these symmetries and also with these other two equations coupled with the Einstein equations, which the second one in this system is the Tolman equation, and the third one is the Klein equation. These two are a generalization of respectively the zeroth law and the first law of thermodynamics in general relativity. So in addition, we have another equation, the last one here. Because of the symmetries, we have an energy conservation along the configuration. So working with this system, one finds the equation for this dark matter model, where the first one gives us the total mass at a given radius. The second equation is the Tolman-Oppenheimer Volkov equations, where nu is the time component of the metric. And then we have these three equations for the model parameters, one for the degeneracy parameter, for the temperature parameter, and for the cutoff parameter. So one can solve this numerically with appropriate boundary conditions. One has to set a value for the fermion mass and give initial values for the parameters at the beginning of the configuration. So as we search for the most general solution, we allow the degeneracy parameter to be positive. So one finds that at the center of this configuration in the core, the values of the degeneracy parameter are very positive. So the core is in a very degenerate quantum regime. Then these values of this degeneracy parameter decreases until the end of the configuration, where the values are very negative, accounting for a Boltzmannian regimes for the fermions, at the outermost part of the configuration. So here is presented in the plot a family of solutions for different masses of the fermions, and this is a density profile where one can see that on purpose we fitted these profiles to represent the same halo, which we can see here at the outermost part, which happens to be the halo of the Milky Way. This one has to give appropriate boundary conditions, which are represented here in this table, where the last two conditions at 12 kiloparsec and 40 kiloparsec with these total masses, these data are taken from the works of SOFU 2013, and for 40 kiloparsecs from Gibbons and collaborators. So the main difference is in the innermost part of the configuration, where the core with increasing mass particle of the fermions, we have a more denser and compact cores for the configuration. And the range in masses of these fermions extends until 378 keV, which is the last stable configuration until the core collapses from gravitational collapse of the core, which Carlos explained in more detail this morning. So the richness of this model is that it can fit the rotation curve, in this case of the Milky Way halo here. This is in black, we see the component of the dark matter for 56 keV, plus in green the baryon components. So this fit the software data, whilst at the same time here in the innermost part, in the maximum of this rotation curve, we define the core, the location of the core. So this can explain the dynamics of the S-star cluster. This more detail on this can be found in the work of Becerra Vergara and collaborators 2020, and also the same authors for 2021 with the fit of the best resolved 17 stars of the S cluster. So with this, in this space-time, let me talk a little about geodesics. So for elliptical orbits and under these symmetries, one has two constants of motion, which are the angular momentum per unit mass of the particle and the energy per unit mass of the test particle. And with the values of the radius at pericenter and apocenter, these two quantities are completely defined. So working with the geodesic equations, one can find a radial equation, and from it identify an effective gravitational potential given by this expression below. And in this graphic, we have plotted different gravitational potential wells in particular for a model for 56 keV in the mass of the fermions, and for different values of the angular momentum. So with this, one can perform a qualitative analysis of the stability of orbits in this configuration. And since this is a regular solution, one finds that for every value of the angular momentum, there is always a minimum of the potential. So there is always a stable circular orbit. In this case, the vertical dashed line here is the location of the core for this 56 keV configuration, and is about 1,000 Schwarzschild radius. So here is the system of the geodesic equations, which simplifies greatly because of the symmetries, and one can solve these equations numerically with appropriate initial conditions. In this case, we chose the start of the motion of the test particle at the apocenter. So the first radius would be the radius at apocenter, the coordinate angles would be 0, and the radial velocity also 0. So with 2 consecutive passages for the apocenter in this case, we can compute this difference in the coordinate angle, and if this orbit were strictly closed, this difference would yield 2 times pi. So subtracting 2 times pi, we can obtain the angle precession for this test particle in these symmetries. And we want also to compare it with the canonical case of a Schwarzschild black hole, which for its precession, we have the more familiar solution here, this expression, which depends on the mass of the black hole and 2 orbital parameters. And it has the particularity that this angle precession is always prograde. So we did this in particular for this calculation for the S2 star. Here are the main results. In this table, we see that for a narrow range in particle mass of the fermions from 55 to 60 keV, we find that the angle precession in the real orbit here in this column ranges from minus 26.38 arc minutes per cycle to very positive values, 9.8 approximately arc minutes per cycle. So we can see that we can have 2 possible outcomes depending on the particle mass of the fermions. We can either have retrograde precession, which was found to be for masses lesser than 55.4 keV, or prograde precession for masses above that value. So here we see in this plot that we have a strong nonlinear growth of the angle precession that is highly dependent on the mass of the fermion particles. So, and this can be explained qualitatively by 2 overall effects. One that produces direct precession and is caused by the quantum core inside the orbit, and the other opposing effect, the opposite effect is due to the extended mass that fills the orbit of the star from the pericenter to the apocenter. So these 2 effects are are competing, and we also computed the extended mass fraction that will be the extended mass, which is given by this integral over the core mass, the mass of the core. So this is represented also here in this column of the table. We can see that for the same narrow range in particle mass, the extended mass fraction ranges over 2 order of magnitudes. So this causes a strongly nonlinear growth of the angle precession with the particle mass. And these 2 overall effects are not independent, because as we've seen earlier, with increasing particle mass, we have more and more compact cores. So consequently, the extended mass fraction, the extended mass that can fill the orbit of the star is it has to be less. So these are related effects. Here we show the orbit of the S2 star in the plane of the sky. So this is right ascension and here the declination for 3 different models. In red, we have a dark matter model of 56 keV, which, if you recall, it has a retrograde precession. In black, the black hole, which for the S2 star gives prograde precession of about 12 arc minutes per cycle. And in green, another dark matter configuration for 58 keV, which has also prograde precession. So in these right panels, we can see a zoom of the pericenter passage and above the apocenter passage. And the main result here is that we cannot, with these few data here that are taken from Do and collaborators, we cannot discriminate between these 3 models if it has a retrograde or prograde precession. So hopefully in the next apocenter passage of the S2 star, that will be approximately in 2026, new data with a better astrometric precision will help us discriminate these between these models, or further constrain the range on the mass on the particle masses. And this effect that I was telling you, it can be greatly quantified here. We have the right ascension versus time for the narrow window just before, just after pericenter passage, where we can see that in the left panel we have the black hole model, and in the right panel dark matter model with retrograde precession. For these few data points with large error bars, it's not possible to discriminate from these 2 possible outcomes. So so to conclude, I wanted to emphasize that unlike the Schwarzschild black hole case, where we have only prograde precession, for this model of the dark matter model, we can either have prograde or retrograde precession. And one interesting thing that is that for the critical configuration that is of 378 keV, the angle of precession for this configuration tends to that of the black hole. And well, these 2 effects, these 2 outcomes are because of these 2 overall effects. Prograde precession due to the compact core at the center of the inside the orbit, and retrograde precession caused by the extended mass that can fill the orbit between pericenter and apocenter of the star. Another thing that we can do to constrain this range in particle masses is study another members of the S cluster. For example, the stars S62 and X4714 have smaller pericenters than that of the S2 star, almost by an order of magnitude. So if these results are confirmed, because for this data we only have the astrometric position, not the radial velocities. If this is confirmed, the range, the capacity of the core in order to lie completely inside the pericenter of these 2 stars would have to be the fermion mass about 100 keV. Another point, well, as I said, is that we hope that in the next apocenter passage of the S2 star, approximately in 2026, with better astrometric data of this passage will help us discriminate and further constrain the mass range of these fermions. And as last and exciting result, a new result that Carlos showed today earlier, also this dark matter cores also can generate a shadow which is very similar to the shadow of the black hole case. So I don't know if you saw the figures of his talk today, but we are very excited about this, and we are looking forward to continue investigating more about that that topic. So that's all. Thank you. Okay.
Thank you very much, Valentina, for this detailed and nice talk. And well, let's see if we have time for questions. We have like 9 minutes for questions. So if there are anyone in the audience that want to comment or question. Yes, Jorge, please.
No, another question. I would like just to congratulate Valentina and thank her because for this wonderful presentation was really very clear. Because you know, this presentation was supposed to made by me, but I can't do it at this moment at the hospital. But you made a really wonderful job. So I will just want to tell you that. Thank you very much. Thank you very much.
Thank you. Thank you. I was delighted to do this.
Yes,
it's my first talk, so it was fun.
Yes, it's very nice, and we wish you all the best, Jorge, for you and for your recovery. I hope you really recover soon. I think you have done also quite an effort to be present in all these presentations. We hope you the best, honestly. Okay, is there any other question? Maybe I have a
Carlos,
comment.
Can I ask something to Valentina? If she can,
yes, sure.
Can tell us a little bit what is the plan? What is what you are planning to do with the model? I mean, what kind of calculations are you planning to do in the next future? Thank you.
Well, now we are fully focused on this new result of the shadow for this core, but with these precision calculations, we are looking forward to do this for different stars, especially those stars which has smaller apocenters, and looking forward for if there is more available data in the near future to further complete or extend this analysis.
Yes, yes. So yeah, Valentina, I think you are referring to the Pasker study, the so-called faint S-stars. Yeah, so just I would like to make a comment on that because I think it's quite interesting. That probably many people knows, of course, the S2 star, the one who has better constraint, much better than the photons, probably that many people don't know, but the best dynamical tracer up to now of the central mass of our galaxy are the S stars, because they have full orbits, more than one period, quite good resolution, precision. there have been evidence the gravitational redshift and precession effect. So this is a fact, and now, of course, it will be very interesting to see inside, bit by bit. Of course, the photons can lay even more inside, but photons are tricky observation, very difficult observations, which GHD has just started to put the first result. But it is very interesting also to look into stars, so real stars, also in gas, dust enshrouded stars like the G stars and these faint stars, because they can achieve very centers of order 100 Schwarzschild radii. And of course, these data are not yet covered a full period, but once we have more and more data, we will be able to really see the precession of these innermost stars, which will really put in test the singularity or the black hole paradigm or more highly compact concentration of matter. Okay, thank you very much, all the speakers, and to Valentina. And I think if there are no other comments, we should stop here. Yes, we're a bit before the coffee break. I think, please, Piero, you remember, I think this is the last talk of the afternoon, right?
Thanks so much.
This looks like, right? Yes.
Yes.
Yes, thank you. I was just now entering that, but yes. Okay, so see you tomorrow. Now tomorrow we move topic to AGN, and there will be mainly for online from Pescara and Rome, and so we leave this today. And so yes, it was a pleasure to be with you. And well, see you next time then.
Bye. All the best to Jorge.
Yes.
Bye.
Thank you very much. Bye.
Toda la fuerza, Jorge. Bye.